Welcome to today's session. In this video, we'll explore an exciting problem, longest turbulent subarray. We'll dive into the problem statement, analyze potential approaches, and learn step by step how to solve it efficiently. Let's get started. In this problem, we are tasked with finding the length of the longest turbulent subarray within a given integer array called ARR. A subarray is considered turbulent if the comparison signs between adjacent elements alternate. For example, one element is greater than the next, and then the next is less than the one after that, and so on. Mathematically, this means that for any subarray I plus 1 j to be turbulent, the following condition must hold for every index k with I equals k less than j, either k plus 1, and k plus 1 k plus 2, or k plus 1, and k plus 1 k plus 2. If the subarray is of size less than 2, it is automatically considered turbulent. The goal is to calculate the length of the longest subarray in ARR that satisfies this turbulent property. Let's consider an example to better understand the problem. Suppose the input array is ARR equals 9 4 2 10 7 8 8 1 9. The output for this input is 5. To explain why, the longest turbulent subarray here is 4 2 10 7 8. Within this subarray, the comparisons alternate, 4 2, 2 10, 10 7, and 7 8. Each consecutive pair alternates between greater than and less than. This pattern gives us a turbulent subarray of length 5, which is the longest such subarray in this input. Now, take a look at another example. Here, the input array is ARR equals 4 8 12 16. The output for this case is 2. The reason is that the comparisons throughout this array are consistent, meaning they do not alternate. Specifically, 4 8, 8 12, and 12 16. Since there are no alternating signs, the longest turbulent subarray consists of any two consecutive elements, such as 4a8. Therefore, the length of the longest turbulent subarray is 2. In the next example, the input is ARR equals 100. Here, the output is 1. This is because the array contains only one element, and as per the problem's definition, a single element is always considered a turbulent subarray by default. Thus, the length of the longest turbulent subarray is simply 1. Additionally, the constraints of the problem specify that the input array will always have at least one element, so this edge case is valid. Finally, let's highlight a few important notes and edge cases. For example, if all elements in the array are identical, such as 5 5 5 5, the longest turbulent subarray will have a length of 1 because there are no comparisons to alternate. On the other hand, if the array features alternating comparisons, such as 1 3 2 4 3, the turbulence naturally extends throughout such a sequence. Here, every comparison alternates, making the entire array the longest turbulent subarray. Understanding these edge cases will help you better approach and solve this problem. To begin solving this problem, we considered the brute force approach. The intuition here is straightforward. We check every possible subarray in the input array to determine if it is turbulent. A subarray is turbulent if the signs of the comparisons between its adjacent elements alternate. To implement this, we would use two nested loops to iterate through all possible subarrays. For each subarray, we would verify if it is turbulent by iterating through the elements again to check the alternating comparison pattern. While this method is simple and easy to understand, it is computationally expensive. The time complexity is n cubed, because we have one loop for the starting index, another for the ending index, and a third to check the turbulence condition. Although the space complexity is 1, the high time complexity makes this approach impractical for larger arrays, as it would take far too long to process all the subarrays. For this reason, we decided not to use the brute force approach. Instead of using a brute force approach, we considered an optimized sliding window technique. The main intuition here is to dynamically track the current turbulent subarray as we traverse the array. A turbulent subarray alternates between greater than and less than comparisons, so we can use this property to guide our algorithm. By comparing three consecutive elements, we determine whether the current subarray maintains the alternating pattern. If the pattern breaks, we reset the window and start tracking a new subarray. This approach involves initializing two pointers, one to mark the start of the current subarray and another to traverse the array. If the alternating condition is satisfied, we extend the subarray, otherwise, we reset the start pointer. Throughout the traversal, we update the maximum length of any turbulent subarray encountered. This method is far more efficient than brute force. Since we only traverse the array once, the time complexity is O(n), and the space complexity remains O(1). The sliding window approach was attractive due to its efficiency, but we opted for a variation called the two-pointers plus state tracking approach. This method simplifies the implementation by avoiding explicit window management. Instead, we use two counters, up and down, to track the turbulent states. If the current element is greater than the previous one, it extends an up turbulent subarray, so we increment the up counter and reset the down counter. If the current element is smaller, it extends a down turbulent subarray, so we increment the down counter and reset the up counter. If neither condition is met, both counters are reset to 1. This approach dynamically tracks the turbulent states and calculates the maximum length during the traversal. By focusing on the current relationship between elements, we avoid the overhead of managing window boundaries explicitly, making this approach both simple and effective. The algorithm for the two-pointers plus state tracking approach is straightforward. First, we initialize the up and down counters as well as a variable max_length to store the maximum turbulent subarray length. Then, we traverse the array and update the up and down counters based on the relationship between consecutive elements. For example, if the current element is greater than the previous one, we increment up and reset down. If it is smaller, we increment down and reset up. At each step, we update max_length by taking the maximum of the current up and down values along with the previous maximum. At the end of the traversal, we return the final value of max_length. This algorithm is optimal because it processes the array in linear time, O(n), and uses only constant space, O(1). This makes it highly efficient and well-suited for large inputs. When comparing the different approaches, there are clear trade-offs. The brute force approach is conceptually simple but computationally expensive, making it unsuitable for large inputs due to its O(n)³ time complexity. The sliding window approach is efficient and intuitive, but it requires careful management of window boundaries, which can add some implementation complexity. The two-pointers plus state tracking approach, on the other hand, combines the efficiency of the sliding window method with a simpler implementation. By directly tracking turbulent states with counters, it avoids the overhead of managing explicit windows and performs optimally in both time and space. For these reasons, we selected the two-pointers plus state tracking approach as our final choice. It balances performance and simplicity, making it the most effective solution to this problem. To solve the problem of finding the longest turbulent subarray, we need to understand what makes a subarray turbulent. A subarray is turbulent if the comparison signs between adjacent elements alternate strictly between greater than and less than. For instance, in the array 9, 4, 2, 10, 7, the subarray 4, 2, 10, 7 is turbulent because 4, 2, 2, 10, and 10, 7. A brute force approach to solve this problem involves iterating through all possible subarrays of the input array, checking each subarray to ensure it satisfies this alternating property, and then keeping track of the maximum length of such subarrays. This method, while straightforward, requires exploring every possible subarray and verifying its turbulence, making it computationally expensive. Let's break it down step by step. First, we use two nested loops to generate all subarrays. For a given starting index, we extend the subarray by incrementing the ending index. Next, we check whether the subarray satisfies the turbulent condition by iterating through its elements and verifying that adjacent comparisons alternate between and. If the condition breaks, we stop checking that subarray. Finally, if a subarray is turbulent, we calculate its length and update our maximum length tracker. At the end of this process, the maximum length we've recorded is the result we return. The brute force approach, while simple, comes with a significant computational cost. To generate all subarrays, we use nested loops, which take O(n)² time. Then, for each subarray, we check its turbulence, which requires O(m) time, where m is the subarray length. In the worst case, this leads to an overall time complexity of O(n)³. However, we can derive some key insights from analyzing this approach. First, the turbulent property depends only on the signs of differences between adjacent elements, meaning we could potentially check turbulence more efficiently. Second, the brute force method involves a lot of redundant work, as overlapping subarrays are repeatedly checked. For instance, when examining subarrays that share the same starting point, we're recalculating turbulence for overlapping segments. Addressing these inefficiencies by reusing intermediate results could significantly reduce the computation time, paving the way for a more optimized solution. To overcome the inefficiencies of the brute force approach, we can use a sliding window technique. The intuition is to maintain a dynamic window that keeps track of the current turbulent subarray as we iterate through the array. First, we initialize two pointers, start and end, to represent the current window, and a variable max_length to store the length of the longest turbulent subarray found so far. Initially, max_length is set to 1 since the smallest subarray has a length of 1. We then loop through the array, expanding the end pointer one element at a time. For each new element, we check whether the turbulent condition holds between it and the previous element. If the condition is satisfied, the current window length is updated to end start plus 1, and we update max_length if this new length is longer. If the condition breaks, we reset the start pointer to begin a new potential window. This approach also handles edge cases like arrays with a single element, which are trivially turbulent, or arrays with all identical elements, which are not turbulent. At the end of the loop, the max_length variable contains the length of the longest turbulent subarray. The sliding window approach is highly efficient because it processes the array in a single pass, achieving O(n) time complexity. This improvement comes from the fact that the window dynamically adjusts without recalculating turbulence for overlapping segments, as was the case with the brute force method. The space complexity is O(1), since we only use a few variables start, end, and max_length to maintain the state of the algorithm. Sliding windows inherently reuse results, allowing us to extend or contract the window dynamically rather than recomputing turbulence for every new subarray. This avoids redundant work and makes the algorithm optimal. Additionally, edge cases such as arrays with duplicate elements or very small sizes are handled seamlessly, as the algorithm adjusts the window based on the turbulent condition at each step. By processing each element exactly once and tracking only the essential information, the sliding window method represents a significant optimization over brute force. Let's walk through an example to see the sliding window approach in action. Consider the array 9, 4, 2, 10, 7, 8, 8, 1, 9. We start with start equals 0, end equals 0, and max_length equals 1. As we expand the end pointer, we check the turbulent condition at each step. At end equals 1, the subarray 9, 4 is turbulent, so max_length becomes 2. At end equals 2, the subarray 9, 4, 2 is turbulent, and max_length updates to 3. When end equals 3, the subarray 9, 4, 2, 10 is turbulent, so max_length increases to 4. This continues until end equals 5, where we find the subarray 4, 2, 10, 7, 8 with a length of 5. However, at end equals 6, turbulence breaks due to consecutive identical elements. We then reset start to adjust the window and continue checking. By the end of the array, the longest turbulent subarray has a length of 5, and that is the result we return. Explanation here. This is the Java implementation of the longest turbulent subarray problem, directly mirroring the Python logic. The Java solution includes type declarations and follows standard Java conventions, such as using the math.max method for comparisons. The code iterates through the array and calculates the maximum length of a turbulent subarray based on alternating comparisons, ensuring efficient performance with O(n) time complexity. Here, we start by analyzing the input array 9, 4, 2, 10, 7, 8, 8, 1, 9. The length of the array is n equals 9, and we initialize both max_length and current_length to 1. Now, we move into the iteration. At I equals 1, we compare ARR 1 equals 4 with ARR 0 equals 9. Since 4 9 but the index I is even, this does not meet the turbulence condition, so we reset current_length to 1. At I equals 2, we compare ARR 2 equals 2 with ARR 1 equals 4. Here, 2 4 and the index I is odd, which satisfies the turbulence condition. We increment current_length to 2 and update max_length to 2. Moving on to I equals 3, we compare ARR 3 equals 10 with ARR 2 equals 2. Since 10-2 and the index I is even, turbulence continues. We increment current underscore length to 3 and update max underscore length accordingly. At I equals 4, ARR 4 equals 7 is compared with ARR 3 equals 10. Here, 7 10 and the index I is odd, so the turbulence condition is satisfied again. We increment current underscore length to 4 and update max underscore length to 4. At I equals 5, we compare ARR 5 equals 8 with ARR 4 equals 7. Since 8 7 and the index I is even, we have turbulence. We increment current underscore length to 5 and update max underscore length to 5. However, at I equals 6, ARR 6 equals 8 is equal to ARR 5 equals 8, so the turbulence breaks. We reset current underscore length to 1. Next, at I equals 7, we compare ARR 7 equals 1 with ARR 6 equals 8. Since 1 8 and the index I is odd, turbulence resumes. We increment current underscore length to 2. Finally, at I equals 8, ARR 8 equals 9 is compared with ARR 7 equals 1. Here, 9 1 and the index I is even, so turbulence continues. We increment current underscore length to 3. After iterating through the array, the longest turbulent subarray has a length of 5, which is our result. Now, consider the input array 4 8 12 16. The length of this array is n equals 4, and we initialize both max underscore length and current underscore length to 1. As we begin iterating, at I equals 1, we compare ARR 1 equals 8 with ARR 0 equals 4. Since 8 4 but the index I is even, this does not satisfy the turbulence condition, so we reset current underscore length to 1. At I equals 2, we compare ARR 2 equals 12 with ARR 1 equals 8. Since 12 8 and the index I is odd, there is still no turbulence, and we reset current underscore length to 1 again. Finally, at I equals 3, we compare ARR 3 equals 16 with ARR 2 equals 12. Since 16 12 and the index I is even, there is no turbulence here either, and current underscore length remains 1. As a result, the longest turbulent subarray in this case is of length 1. For the final example, the input array is 100. Here, the length of the array is n equals 1, and we initialize max underscore length to 1. Since the array contains only one element, no iteration is needed. By definition, a single element array is considered to have a turbulent subarray of length 1. This brings us to the key steps of the algorithm. The approach uses a sliding window to analyze turbulence by comparing adjacent elements. We track the current turbulent subarray length with current underscore length, while max underscore length stores the longest one found. A turbulent relationship alternates between greater than and less than comparisons. If turbulence breaks, current underscore length resets to 1. The algorithm handles all scenarios, including increasing, decreasing, constant values, and single element arrays, with an efficient time complexity of O(n). To analyze the time complexity, we start with the initialization of variables. We define n as the length of the input array, and max underscore length and current underscore length to track the results. These initializations are constant time operations, O(1), as they don't depend on the size of the input. Next, there's a check for whether the array has only one element. This conditional check is also O(1). The main work happens inside the single traversal of the array, which uses a for loop running from index 1 to n1. Within each iteration, we evaluate whether the current element satisfies the turbulent condition. This involves basic arithmetic and logical operations, such as comparisons and modulo calculations, all of which are O(1). Updates to current underscore length and max underscore length are similarly O(1). If the condition is not satisfied, resetting current underscore length is another O(1) operation. Since this loop executes n1 times, the total contribution is O(n1), which simplifies to O(n). Therefore, the overall time complexity is primarily determined by this loop, making it O(n). After the loop finishes, the algorithm concludes with a return statement that outputs max underscore length. Returning a value is a constant time operation, O(1). Combining all the steps, the algorithm's total time complexity is O(n), because the loop dominates the runtime. Moving on to space complexity, the algorithm uses a constant amount of additional memory. The input array, ARR, is passed to the function, but it doesn't require any extra space since we're not making any modifications to it. The variables n, max_length, current_length, and I are scalar values, and each of them uses O1 space. Since we're not allocating memory for additional data structures or performing recursive function calls, the total space complexity is O1. No extra data structures are introduced in this solution, and the algorithm operates entirely in place, ensuring minimal memory usage. This results in an overall space complexity of O1. Comparing this approach to a brute force method highlights its efficiency. A brute force solution would involve generating every possible subarray of the input, which requires O(n²), operations to create the subarrays and up to O(n) operations to verify the turbulence condition for each one. This would lead to a staggering O(n³ time complexity. The current approach avoids this inefficiency by dynamically checking the turbulence condition in a single pass, reducing the time complexity to O(n). Furthermore, the space complexity is also reduced from O(n²), or higher in a brute force solution to O1 in this optimized approach, making it far more suitable for large inputs. To better understand the performance, let's examine the best, average, and worst-case scenarios. In the best case, the array might contain identical elements or the turbulence condition could be broken immediately after the first comparison. While the loop still iterates through the array, there would be minimal updates to current_length. Thus, the time complexity remains O(n), and space complexity is O1. For the average case, the input array may have a mix of turbulent and non-turbulent sequences. The loop processes the array linearly, with updates to the variables depending on the condition. Again, time complexity is O(n), and space complexity is O1. The worst case occurs when the entire array forms a turbulent subarray. For example, if alternating elements consistently satisfy the condition, the algorithm performs the maximum number of updates to current_length. Even in this scenario, the algorithm processes the array in a single pass, maintaining O(n) time complexity and O1 space complexity. To solidify our understanding, let's provide a mathematical justification for the time complexity. The algorithm's key operation is the single traversal of the input array. The number of iterations in the loop is proportional to the array's length, n. During each iteration, a constant amount of work is performed, including comparisons, arithmetic calculations, and updates to variables. Since there are no nested loops or recursive calls, the total work is calculated as O(n) iterations multiplied by O1 per iteration, resulting in O(n). The absence of additional memory allocation confirms the O1 space complexity. In conclusion, this algorithm is optimal for the problem, achieving a linear time complexity of O(n) and a constant space complexity of O1. This efficiency makes it highly effective for large inputs, meeting the constraints typically seen in competitive programming platforms like LeetCode. When solving the longest turbulent subarray problem, there are a few common mistakes to watch out for. First, failing to handle edge cases properly can lead to runtime errors. For example, if the input array has fewer than 2 elements, such as an empty array or a single element array, your solution might attempt to access indices that don't exist. To fix this, always account for these edge cases by checking the array length upfront. Another common pitfall is incorrectly comparing adjacent elements. The turbulent condition requires strict alternation, like ARR, I1, ARR, I plus 1, but misunderstanding the precedence of the operators or the logic can lead to errors. Using parentheses can help ensure the comparisons are evaluated correctly. Lastly, overlooking reset conditions is another frequent issue. If the turbulent property breaks at any point, the count or window must be reset, otherwise, your results may be inaccurate. These resets are critical to maintaining the integrity of your solution. Another area where mistakes often occur is using brute force inefficiently. Trying to explicitly check all possible subarrays results in a time complexity of O(n³), which is far too slow for larger inputs. Instead, you should aim for optimized approaches like sliding windows or two-pointer techniques, which can reduce the complexity significantly. Additionally, ignoring equal consecutive elements can be problematic. If two adjacent elements are the same, such as RR(i) equals RR(i plus 1), this violates the turbulent condition and must be handled explicitly. A good fix is to reset your window or skip over these elements to ensure they don't interfere with the logic of the solution. Recognizing these inefficiencies and addressing them appropriately can greatly improve both the correctness and performance of your implementation. Now, let's consider some key insights that are particularly useful in interview settings. First and foremost, make sure you fully understand the problem statement. Clarify what is meant by turbulent and confirm any edge case scenarios with the interviewer, such as arrays with identical elements or minimal lengths. Once you've established a clear understanding, it's a good idea to start with a brute force solution. This provides a simple baseline and opens the door to discussing optimization strategies like sliding windows or dynamic programming. Throughout the interview, explain your thought process clearly, be sure to highlight how you deal with edge cases, identify patterns, and justify your choice of techniques. Lastly, test cases are critical. Use sample inputs to demonstrate the correctness of your approach, especially for tricky edge conditions. This not only showcases your solution's robustness but also reinforces your problem-solving skills to the interviewer. To deepen your understanding, it's helpful to look at related problems that share similar patterns. For instance, the longest increasing subsequence problem, LeetCode 300, focuses on finding a strictly increasing sequence, which can give you insight into using dynamic programming. Another related problem is wiggle subsequence, LeetCode 376, which also involves alternating differences between consecutive elements. This problem is especially relevant because it mirrors the turbulent condition. Then there's the longest subarray with absolute difference less than or equal to limit, LeetCode 1438, which is a sliding window problem that emphasizes constraints on subarray properties. Finally, subarray product less than k, LeetCode 713, is another sliding window problem that can help you refine your approach to managing subarrays efficiently. When tackling these problems, it's important to weigh the trade-offs between different approaches. For example, a brute force solution, though simple, is rarely efficient. On the other hand, a sliding window approach, while faster, requires careful handling of edge cases to maintain correctness. Dynamic programming is another powerful approach to solving this problem efficiently. By maintaining two states, one to track up turbulence and another to track down turbulence, you can systematically evaluate each element's contribution to the turbulent condition. This method offers a time complexity of O(n), while providing a structured way to handle transitions between states. However, it can be slightly more complex to implement compared to sliding window methods, as you need to carefully manage these states at each step. The trade-off is that dynamic programming can sometimes be easier to debug since the logic is more explicit. Choosing between sliding window and dynamic programming often depends on your comfort level and the specific constraints of the problem, but both approaches are highly efficient and well-suited for this challenge. And that's a wrap. We solved the longest turbulent subarray problem using an efficient sliding window approach. Remember the key concepts we discussed, and try practicing similar problems to strengthen your understanding. Thank you for watching, and don't forget to like, subscribe, and stay tuned for more coding tutorials. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!